Hello, everyone. Can you hear me?
Oh, yes.
Yes.
Okay, so today we are going to start the topic matrix algebra. Actually, you remember from the book by textbook, okay? From the textbook, uh, earlier in the last two sessions, we covered the chapter 1. Okay, in chapter 1, we covered the section 1-1 and 1-2. And then later on, and the other two sections on this chapter 1, 1-3 and 1-4 were not included, okay, in our course. So we skipped those. So after that, then in chapter 2, I have provided some lecture on Moodle and on YouTube. So 2-1, 2-2, and 2-3. So the topics are vectors, spans, and the independence, checking the independence of vectors. So out of these, I have already uploaded the material about vectors and spans on Moodle and on YouTube. So I would recommend you to look at those videos, okay, on the YouTube. And then later on today, I will also upload about for the section 2-3 for the independence of vectors on the YouTube. Okay, so then after that, there is this chapter 3, okay, chapter 3. So in chapter 3, now there are some topics. First one is the vector, no, sorry, transformation. Okay, you can say that vector or linear transformation, something like this. Where is this eraser? A transformation. Okay, transformation. Okay, so that is section 3-1. So
Sorry, you said
three,
you skipped one section, yes?
sorry?
You said that you skipped one section?
Skipped one section? Yes. 1-3 and 1-4, they are not included. But I did not skip any other thing. So this is already available on Moodle. This is already available on Moodle. This will be available later today. Okay, and then this will be also available later today. Okay, and then today I'm going to start in this class matrix algebra. Okay, matrix algebra. Okay, so that is section 3-2. So this is in the class. Okay, during the lecture time. And then after that, of course, we can there will be the topic for the finding the inverse of matrix, inverse or inversing the matrix, inversing matrices. Okay, so this is topic 3-3. So we will cover it. And then after that, there will be the LU factorization. LU factorization. Okay, 3-4. So we will cover all this thing. Okay. And in chapter 3, there will be another chapter, which is 3-5 on Markov chains. That is not included. Okay, that is optional, so it is not included. In fact, the book also says that LU factorization is also optional, but I think it's interesting and then very much related with the previous topic, so we will include it. Okay. So this is up to now, okay? And then later on, when the time comes, I will explain about the other chapters, what we have to cover and what we are not going to cover. Is it clear?
Yes.
Okay. Okay, so now let's start the topic today, matrix algebra. Okay, so in the matrix algebra, we have to learn some key points. In fact, many of those key points you may already know from some your earlier mathematics classes. So I don't have to go into much details about these. So for example, uh, you know that what is a matrix, okay? So we know that what is a matrix and what is the order of matrix, okay? And or in another word, what is the dimension of matrix, okay? Dimension of matrix, okay? So actually, matrix is an array of numbers, okay, or variables, okay, in something like this, in this form, okay, in the in the rectangular format, in the form of the rows and columns, we arrange those numbers. So this is the matrix, okay. So these elements of the matrix can be variable, can be constants, it can be functions as well. But okay, for this purpose, we will mostly be dealing with the numbers, so the real numbers. So what is the order of the matrix or the dimension of the matrix? Order of the matrix, or in another way, dimension of the matrix is the number of rows and columns. So number of rows times the number of columns, okay? So for example, if there is a matrix which has 3 rows and 3 columns, so that matrix will have a dimension of 3 by 3. Okay. Or in another word, if the rows and columns are equal, so we can also say that it is an third order matrix. But of course, normally we use the term dimension of the matrix. So you also know that we can add one matrix with another matrix, okay, to another matrix, okay. So provided the dimensions of both matrices are same. So for example, you can add a matrix with the dimension of 2 by 3, that is 2 rows and 3 columns with the matrix which will have 2 rows and 3 columns, okay? And then the elements of the matrices will be added term by term, element by element, okay? Matrices will be added element by element, and that addition process is a commutative, whatever you say. You can reverse the direction, or it is also distributive or something like this. So if the dimensions of the matrices are not same, so for example, if there is one matrix which is a 2 by 2 matrix and another matrix which is a 2 by 3 matrix, so then we cannot add them, okay? Cannot add those matrices, okay? Although in more advanced computer programs such as MATLAB, etc., you still can add these two matrices. But in those cases, those matrices are considered as arrays, and only those corresponding elements are added, and those corresponding elements are not added. But of course, from the mathematical point of view, we only are considering those matrices which will have the same dimensions. They can be added together. So then also the matrices can be multiplied by a scalar. So for example, scalar can be a number. So scalar can be multiplied with the matrix. So in this case, all the elements of the matrices are multiplied by the scalar. So if the scalar is C and the matrix elements are represented by A's, so all terms will be, all A terms will be multiplied by the scalars, okay? Something like this. So scalar multiplication is also defined. And then we quickly move to some types of matrices. one of the matrix is called as the identity matrix. So identity matrix is a matrix which has all the elements as 0 except those elements which are on the diagonal. So for example, if I write a 3 by 3 identity matrix or identity matrix of order 3, so this will be the matrix. So in this case, the matrices on the diagonal of this matrix are all 1, and then all the other elements will be 0. So any matrix which can be so the property of the diagonal matrix, the property of this identity matrix is that it serves in a similar manner as number 1 in arithmetic. So if we have a matrix which has the same dimension as the identity matrix, so we can multiply that matrix by the identity matrix, and then we will get the same matrix. So for example, if A is a 3 by 3 matrix and I is a third also 3 by 3, of course, matrix, so then AI will be equal to IA, or it will be equal to A. So identity matrix can be multiplied with the other matrix, and then it will result into that matrix as well. But what I forgot to mention over here is that the multiplication of matrices, multiplication of matrices. So a matrix A can be multiplied with another matrix B, provided that the the columns of A, the number of columns of A, the number, okay, this is the symbol for number of columns of A are equal to the number of rows of B. Okay, so for example, if A is an n by m matrix, okay, in dimension, then B should have m by some other number, or n whatever, m by L, we can say m by L matrices. So here m is the number of columns of A, B is the number of here m is the number of rows of B. So these should be equal. If these are different, then AB cannot be performed. AB process cannot be performed. So generally speaking, the AB is not equal to BA. So the multiplication should be performed in a specific order. Okay, so when you multiply A with B, and then, or in another word, if you multiply B with A, suppose that both are possible, just like in the case of the square matrices. But generally speaking, AB will not be equal to BA. Okay, so therefore the multiplication of the matrices is not commutative. So this type of property is called the commutative property. So for example, if AB is equal to BA, so then that type of property of the two numbers or two matrices is called as the commutative. But since it is not equal, so this type of commutative property does not exist in the matrices. So we can see it with the help of some examples, and then I will also explain some other examples. So maybe I can move to some of the examples. Okay. Okay. So example for the illustration. So suppose if we have column A as 2, 0, minus 1, 3. Okay. Sorry, it is not column, it is matrix. So suppose matrix A is 2, 0, minus 1, 3, and matrix B is 4, 1, minus 2, 5, and 0, minus 1. And suppose matrix C is minus 4, 1, 0, 2. And D is 2, 1, 0, 0, 4, 2. Okay, E is 2, minus 3, and then F is 4, minus 1. So what is the order of this matrix A, or dimension of this matrix A? It is a, yes. What is the order of matrix A?
2
by 2.
It is a 2 by 2 matrix. How about B?
2 by 3. 3 by 2.
3 by 2. And C?
2 by 2.
2 by 2. And how about D?
2 by 3.
Okay, and E?
1 by 2.
1 by 2. And F?
2 by 1.
2 by 1. Okay, so can we determine A plus C? So what will be A plus C? A plus C will be the addition of A and C, and then the addition will take place element by element. So it will be 2 minus 4, 0 plus 1, minus 1 plus 0, and 3 plus 2. So A plus C will be minus 2, 1, minus 1, 5. Okay, so can we determine 3 times of B? So what will be 3 times of B?
12.
12.
Minus 6, 0.
Mm-hmm.
3, 15. Minus 3.
Yeah. Okay, so that will be 3B. And what will be E minus D?
We cannot perform.
Cannot determine.
Yes, so not defined. Okay, so we can say not defined or impossible or cannot do. So whatever answer, E minus D. What is AC? So AC is the multiplication of the matrices. So I write A here, 2, 0, minus 1, 3, and C will be minus 4, 1, 0, 2. So AC is performed like this. So you take the first row of A and then multiply element by element, first column of A. Okay, so it will be then 2 times minus 4 plus 0 times 0. Okay, and then that will be the first element of this product matrix. In this case, of course, first of all, we need to check that this is a 2 by 2 matrix, and this is also a 2 by 2 matrix. So here this 2 is equal to this 2. So that means the number of columns of A should be equal to the number of rows of C. Okay, and then only it will be defined. So for the next element, you will take this first row and then you will multiply it with the second column. So this will be the first row and second column element. So it will be 2 into 1 plus 0 into 2. Okay. And then here, tell me the component.
Minus 1.
Minus 1.
Minus 4.
Yeah.
3 to 0.
And here,
Minus 1 to 1. 3 to 2.
yes. So this will be. So in this case, now it will be minus what will be that? -6, right? It will be minus,
-8.
oh, sorry, 8, -8. And then it will be 2,
2.
4, and then it will be also here. What will be that?
5.
No, 5, 6 minus 1 is 5. Yes, 5. So it should be 5. Yeah, it should be 5. Okay, and then how about CA? So whether CA will be same as AC? So that we need to find. So CA, it will be -4, 1, 0, 2, and A will be 2, 0, -1, and then 3. So what will be that? -4 into 2 is -8, -8, and then -1, okay? Minus, that is 0, and 1 into 3 is +3. And then this is 0, and then this is -2. And then this is 0, and then this is 6. So what it will be? -9, -2, 3, and 6. So now we can see that AC is this, okay, but CA is something else. So which means that AC is not equal to CA, okay, in this particular case. We cannot say that in all cases it will be the same result, but generally speaking, AC is not equal to CA. In some particular cases, both can be equal as well, as we will see later on. Okay, so how about, can we determine AD? Can we determine AD? AD is 2 by 2, and then
Yes.
2 by 3.
Yes, we can.
So AD will be 2, 0, -1, 3. So we can determine it as you have answered. 2, 1, 0, 0, 4, 2. So that means here it has 2 columns, here it has 2 rows. Okay, so it is 2 by 2, and then it is 2 by 3. Okay, so we can determine it. So how it will go? 2 by 2 is 4. 2 by 0 is 0. 2 by 1 is 2. 2 by 4 is 8. Sorry, 0 by 4 is 0. Okay? And then 2 by 0 is 0, plus 0 by 2 is 0. And then -1 by 2 is -2, and then 3 by 0 is 0. -1 by 1 is -1, and 3 by 4 is +12. And then -1 by 0 is 0, and then 3 by 2 is +6. So what we get is 4, 10, 0, -2, 11, or 6. If I did not make any mistake, so then it should be correct. So 4, 2, 0, 4, 2, -2, 11, and 6. So this should be, no, this was not 8, this was 0 actually. This was 0. This was 0 because it is 2 by 1 is 1, and 0 by 4 is 0. So it should be 0. Yeah, it is 2. So 4, 2, 0, -2, -11, and 6. Okay, so but can we determine DA?
No.
DA, yeah, so because DA is not defined, okay? Because DA means it will be 2 by 3 and then 2 by 2. So 3 is not equal to 2, okay? So 2 by 3 and 2 by 2. So it is not equal to 3. And how about EF? let me fit everything here. EF, E and F. E, where is E? E is here. E is what? 1 by 2. And how about F? F is
2 by 1.
by 1. So EF is possible. So what will be EF? 2 minus 3 and then 4 minus 1. So what will be EF? EF will be 2 times 4 is 8 and minus 3 times 1 minus 1 is plus 3. So it will be just a single element matrix 11 in this case. So which is evident from this 1 by 1 over here.
Can I ask
Yes?
if we will know the EF and, for example, the F, how we can find E? Is it possible?
If we know F
And EF,
F.
and we need to find E.
We need to find E.
Is it possible?
That is the that is you're talking about the matrix division. Matrix division, although actually matrix division has not been very well defined. Okay, you can do it in the form of for square matrices when you find the inverse. But if you, for example, if you, as you have said that we know EF and we know F, then we cannot find E. Because most text which I have, I think which I have up to now seen is that they do not define the division of the matrices. Okay, so the division of the matrix is something which has not yet been developed up to now. So we cannot find E.
Okay, thank you.
But I think maybe some computer program can do. But I think this is like it's more like an advanced topic. I think, yeah, that is no, there is no. It's not possible at this moment. Actually, we are not considering any matrix division. Okay, so how about FE? So whether we can do FE? How about FE? Is it possible? So F is 2 by 1 and E is 1 by 2. 2 by 1 and 1 by 2. So FE will be 2 by 2 matrix. Okay. So F4 times 2 is 8. Okay. 4 times minus 3 is minus 12. And then minus 1 times 2 is minus 2. And minus 1 times 3 is plus 3. So FE will be a 2 by 2 matrix. Okay. So if we want to find FE. So you can see that EF and FE has different, do not have the same dimensions in this case. Okay. Do not have the same dimensions. Okay, so this was some exercise about the matrix algebra. Okay, next we talk about the transform of a matrix. Okay, transform of a matrix. So what is the transform of a matrix? So the transform of a matrix is a matrix in which, if for example, if we have a matrix A, its transform will be the one in which the rows and columns will be interchanged. Okay, the elements in the rows and columns will be interchanged. So for example, if the elements in matrix A will be AIG, A where ith row and jth column. So and then it's then the elements in its transform, which may be represented by B, will be the elements will be the same elements, but in the jth row and ith column. Okay, so the transform. So in this case, B will be the transform of this matrix A. Okay, B will be the transform of this matrix A. So for example, if I take a matrix A as 1, 3, 7, 4, 0, 9, 1, 1, 3. So its transform will be the one in which I will replace I will take the first column of A as the first row of A transform. So it will be 1, 4, 1. And then second column of A, 3, 0, 1 will be the second row of A, 3, 0, 1. And then the third column of A will be the third row of B. So for example, if it is 7, 9, 3, 7, 9, 3 will be the third row. So here you will see that, for example, this 3 in A was in the first row and second column, but now this 3 has now moved into the second, sorry, it was in the first row and second column, and now it has moved into the second row and first column. So I and J have interchanged, okay, over here, the matrices for the transform matrices. So sometimes the transform of a matrix is equal to the matrix itself. So when sometimes the transform of A is equal to the matrix, original matrix itself. So in that case, that matrix is called as the, what is this matrix called? It is called as the symmetric matrix, okay? It is called as the symmetric matrix. So for example, I can write a symmetric matrix as something like this. So it will be 3, 2, 5, okay? And then it will be 2, 5 here, and then it will be 1, then 2, so 2 will be here, and then it is maybe, you can say 0, okay? So this is a symmetric matrix, because if I take its transpose, so it will be 3, 2, 5, 3, 2, 5, and then 2, 1, 2, 2, 1, 2, and 5, 2, 0, so 5, 2, 0. So which is the same as the original matrix. So these two are the symmetric matrices, because if you take its transpose, and if the transpose is same as the original matrix, so then that is the symmetric matrix. And there is another type of matrix which is called as the skew symmetric matrix. Skew symmetric matrix, okay? So skew symmetric matrix is the one, if we take its transpose, then it will be negative of the original matrix, negative value of the original matrix. So for example, if I take A as something like this, maybe 4, then 0, 5, okay, then it will be 0, minus 5, okay, and then 3, 12, and then it will be minus 12, and then 7. So if I take its transpose, so you will see that it will be 4, 0, minus 5. And then then it will be 0, 3, minus 12, okay? And then it will be what? It will be 5, 12, and 7, okay? So in this case, you can see that the matrix over here have the terms over the matrix are different over here, okay? In fact, I think I made some mistake over here. This is not exactly what I have told over here, because in this case, although the A transpose is the upper terms are negative, but the but the terms on the diagonals are the same. So we cannot strictly say that it is a skew symmetric matrix. So as of now, I think maybe I will just skip it. Okay. I will tell you about this more example later on. Okay. Yeah, skew symmetric matrix. Okay, so anyway, skew symmetric matrix over here, and then we will talk about skew symmetric matrix sometime later on. Okay. Let's apply a, let's do one example, okay? Another example. Another example is, for example, if we have A as 2, 4, 3, and -1, -2, and 4, and then 3, 1, -1, 3, 3, 1, -1. Okay. So if we apply a row operation in this, for example, let's say if we take a row operation in this case to make something like this, 3 times the row 2, okay, plus row 1, and then that will be the new row 1. Okay, well, this is just any row operation which we can perform over here. Okay, I mean, we are not doing like Gauss-Jordan elimination. I just want to illustrate one point. So I just have chosen this row operation. That means I multiply the second row by 3, -3, and then add it to the first row. Okay, and then what we will get. So what I will get over here in place of 2, what I will get?
-10.
Yes, -10. And what I will get over here?
5.
5. And what I will get over here?
0.
0. And then the other terms will be same. 4 -2, 1. And 3, 4, -1. Okay, and now by this row operation, this matrix is equivalent to this matrix. So now I take a identity matrix 1, 0, 0, same 3 by 3. So 0, 1, 0, 0, 0, 1. I take an identity matrix. And for this identity matrix, I apply the same operation. So -3 R2 plus R1 will be R1. So what I will get over here? In the first row.
1.
1. Then
-3
-3, and here
is 0.
0, and then 0, 1, 0, and then 0, 0, 1. Okay, so now I take this transformed matrix and I multiply it with this original matrix. Okay, so I take this transform matrix 1 -3, 0, 0, 1, 0, and 0, 0, 1 is multiplied by this original matrix 2 -1, 3, 4 -2, 1. So 3, 4, -1. So what I will get? So for example, now 1 into 2 will be 2, -3 into 4 will be -12, and that will be the last term, that term will be 0. And then for the second one, 1 into -1 will be -1, and -3 into 2 is plus 6, and the last term will be, that is 0. And then 1 into 3 is 3, and -3 into 3 is -9, and then 0, that will be 0. Okay, so for example, this one, now I will take this second row, so 0, 1, 0, so only this one.
-3 to 1, I guess.
Hmm?
It was
Hmm?
for the element 1, 3, it was 3 minus 3 plus 0.
-3 plus, sorry. Okay, 1.
3 minus 3 plus 0.
Yeah, 1 into 3 and then -3. Yeah, 3 minus 3. So it should be 3. Yes. Okay, so for this now, for the second row will be multiplied with these columns. So only the middle part we can consider, because all others are 0. So 0 into 4 will be, sorry, 1 into 4 will be 4. And then it will be -2. And then it will be 1. And similarly, in this case, for the last one, only the last one we will consider. So 3, 4, -1. So this way, this time, what it will get? We will get 2 minus 12 is -10. 6 minus 1 is 5. And then 3 minus 3 is 0. And then we get 4 minus 2, 1, 3, 4, -1, which is the same as this matrix, So what we have seen from this exercise is that, what we have seen from this exercise is that the row operation which we have actually performed is somehow connected with the identity matrix. Okay, is somehow connected with the identity matrix. So it means that this is called as elementary matrix. We can obtain by the identity matrix by performing the same single elementary row operation. Okay, so although we will not do like this in the all the time, but we can. So we have illustrated over here is that the row operations which we perform on the matrices are the elementary operations which can be also performed on the identity matrices. Okay, so that was one of the point. So there are some other matrices as well. So for example, a diagonal matrix. Okay, diagonal matrix. So diagonal matrix is the one which have only elements at the diagonal. All the other elements are 0. So for example, 3, 0, 0, 0, 4, 3, sorry, 0, 4, 0, and 0, 0, 5. So this is a diagonal matrix. Okay, any power of the diagonal matrix. So for example, if we multiply the diagonal matrix by its diagonal matrix dd, then we will get actually an element that will be d into d, that will be equal to d square. Okay, in this case, only the diagonal elements will be squared. All other elements will still be the diagonal elements. So for example, if we say 3, 0, 0, 0, 4, 0, 0, 0, 5. So 3, 0, 0, 0, 4, 0, 0, 0, 5. So what we will get? So 3 times 3 is 9, and then all other terms would be 0. And then similarly 3, and then we will multiply it with 0. So 4, only 4 will be So 3 times 0 is 0. And then 4 times 4 is 16. Mhm. Okay, wait a minute. Okay, so 3 times 3 is 0, and then all the other terms are 0. 3 times this one, 3 times 0 is 0, plus 0 times 4 is 0. So it will be 0, 0 over here. And then you will get this answer, okay? If you can verify it. So you can see that only the diagonal terms have been squared in this case, okay? So this is the property of the diagonal matrix. Okay, so the next topic is actually the finding the inverse of the matrix, inverse matrix. So I don't have time to complete this topic, but the process, but the algorithm for finding the inverse matrix is that, for example, if we want to find the inverse of matrix, something like this, 1, 2, 1, 3, 1, 1, 4, 0, 3, okay? If we want to find the inverse matrix, so what I will do is I will create an augmented matrix, okay? Over here, 1, 2, 1, 3, 1, 1, 4, 0, 3. And then that augmented matrix will be placed, will be made by appending a unit matrix over here, 0, 1, 0, and 0, 0, 1. And then you will perform the row operations so that on the left-hand side, you will get a unit matrix in this form. And then by this row operations, this right-hand side matrix will convert into a inverse matrix. And what is the inverse matrix? Inverse matrix is the one when it is multiplied by its inverse, then it results into an identity matrix. Okay, so if I will have time, then I will also upload the video about this inverse matrix and for other topics. And then we will continue this linear algebra topic later on. Next week, you will be given one assignment about these linear algebra topics that will be produced by using Mathematica. So the necessary Mathematica commands and information I will also provide. And some of the, I think, tutorials in the form of the PDF have already been also uploaded on Moodle as well. So do you have any question?
No, thank you.
No questions by now.
No questions? Okay. No questions, then I stop this share. And then it's almost time to leave. So, okay, have a good weekend, and I shall see you on next Monday.
Goodbye.
Thank
Thank
you.
you.
Goodbye.
Okay, bye-bye.
Bye.